Okay, I'm going to share my screen. Okay, so as we talk about this already, I just want to repeat it again about this concept that the key point about homework assignment number 3 is for you to develop a way to take a single program, such as what you have done in homework assignment number 2, and we try to break it into 2 parts, which last week we talked about how do we break it into, let me see, the client part and the server part. And such that the functionality equivalence is still the same as the previous slide. Still the logic about the computation and information flow is exactly the same as you would have done in a single program and single process. But we actually now be able to break it up. When we break it up, we broke up both the computation as well as information. Here the information means object. Means no longer we constrain the object to be in one location that's near you. So now we allow the object to be at another location, and we still can perform the computation. And this is the first step. We're going to break the concept of object that's actually being locked down that close to your object-oriented program. Because what object-oriented programming really is really how do you write the program to interact with object. So far until now, we're interacting only with object that locally in your memory. And this homework, we're going to free it up. So it will go to another server across the internet. And later we will actually introduce other concepts such as object mobility or object persistence. Means that the object is not just in your memory, it could be in your file. It could be in a hard disk that's actually on your USB drive. And it's after you finish the program, the object still exists. And then so next time you can just pull it out from your object. So that's you can imagine how important that is for real world application. Okay, so we talk about this scenario between client and server, and today I like to be more generalized and such that this could extend it to not just 2 from client server, but essentially you can do on any number of machine if you want. Okay, in fact that's sounds a lot more complicated, but in terms of software complexity that you have already developed is actually the same. Okay, so that's a good news. So I'm actually going to recap what we say. Okay, so we talk about, we have utilize this concept called shadow object. So we utilize a bunch of things that are provided by object-oriented programming, inheritance that we have here, and we have also something called overloading that we leverage here, and also we use virtual function that's inside here. Not overloading, sorry. Inheritance and the polymorphism, which is the virtual function. So just rephrase that. Virtual function in C++ is their way of realize the concept of polymorphism. Okay, so last time we talked about the concept of casting. So I want to go back to this example because this example help us to really understand why we're doing this. And also this help you to understand the object-oriented paradigms itself. And you will see that what do we mean by encapsulation and polymorphism together, and inheritance, of course. So last time I showed the example about casting. So here you can see I'm actually doing a casting in this particular line. That flies underscore array index I is equal to casting fly star, and then after there is the address of the object SF1. Okay, so here are three things I want to provide a background here. So number one, I define SF1 is a object instantiation, an object instance of shadowfly. So SF1 is a shadowfly object, I mean, to say it in plain English. And F2 is actually an object of flight. Okay, one of them is shadowfly, one butterfly, but remember that shadowfly inherit from flight, which means that abstractively they're both fly. Okay, and therefore I can do a casting in this sense. So you wouldn't be able to, you shouldn't do casting until they have this relationship over here. All right, then I create an array. Let's create an array. I call it fly array. So fly array is an array that I can have, I mean, later I should actually really not use array. In C++, we usually use a vector. Okay, vector is a much nicer way of doing array, but because we haven't talked about vector, I'm using array. Later you will see that I will change the code to the vector interface. So I have a fly array, which is an array of pointer to the fly object. So essentially what we can have here, I'm just draw a picture. You can see that this is a fly array. And one of the element of the array, which is pointer to SF1, which is the shadow fly. And you can see that I have another line of code here, which is a fly array underscore array index J, which is another element of the array, which is actually a pointer to F2, which is a real object. So you can see that I have an array with SF1 and F2. And the thing is that abstractively, both SF1 and F1 are flight. However, the difference is that we really know I mean, I shouldn't say the programmer, but the designer of the system really know there is a possibility that some of this pointer is actually pointing to the derived class of the fly, such as this case for the shadow fly. Okay. All right. So here I'm going to draw the picture to actually see that how this array really works. Okay. So basically for F2, let's look at F2 because it's a simple case, it's easier. That this pointer is pointing to the real fly object, means the object was created as the class flight. Okay, so F2, all right, is over here, while the SF1 is not really a created as a fly, it was created a shadow fly. I'm just drawing a little bit smaller, means that this is a particular kind of object that's actually the purpose was actually redirect to something else. But the size actually might be misleading because in terms of how many bytes of memory to support F2 and SF1, in fact, their memory footprint, SF1 is actually bigger because all the attribute that F2, which is a fly, has, SF1 must have. And it might have some extra thing. So usually the derived class, the object instantiate from the derived class, the memory footprint is usually bigger. Okay, but at this moment, let's not worry about memory footprint. Let's just worry about the role of the object. All right, so before I even move on to the SF1 and F2, there is a very important thing. We look at the application program, I put it here. So application program, what I define application program is the program or piece of code or function that will utilize this array. And this array is, as we saw that before, is an array of pointer to the fly object. Either is the original fly object or the derived fly object. It doesn't matter. The thing about object-oriented principle is that once I define this array, the way I define it, then essentially the application program doesn't need to know whether it's a SF1 or F2. It doesn't need to know whether it's a shadow or not shadow. All they care is that every single element here will support the interface, or what you call fly.h, whatever the attribute member function and member, what we call the interface supported by the fly. That's all I care. So essentially, this is a principle of encapsulation. The encapsulation means that all the detail about exactly those objects was well captured with that notation that I said, this is a fly array. So that's the thing you should now really learn. How do you actually design a system in such that when you have a bunch of objects that you would like to manipulate, you want to interact with, I mean, what is the encapsulation you need to put it there, and such that people who interact with the object you design, and they don't need to worry about detail, they just need to know, oh, what is the abstraction that's appeared to me, which in this case is just flight, okay? And then I would just need to know how to access a fly, get distance, and whatever function, and then I will be able to deal with that, even if this object is not in your local machine, or is actually has a different behavior. That now we introduce polymorphism, because here, if you make the same function call, if that function is a virtual function, then the behavior SF1 and the F2 might be different because of they're from a different, one is from the right, one is from that. Okay, so you can see that this example indeed shows a nice challenge for you to think about how do you design object-oriented way. Okay, so now let's actually see what the SF1, the shadow object, is really doing. So it's not so surprised from the code we can see last Thursday and Friday, those two videos. And it really is just a what I call a forwarding engine. So essentially, the SF1 played two roles. Number one, SF1, at the time it was constructed, it was provided with URL and the object ID, class ID. Those three pieces of information give them the ability to uniquely identify where the object really is right now, which is the object is F1. So basically it provides the URL where F1 is being hosted right now, and what's F1's object identity, what's F1's class identity. And with this three pieces of information, that this SF1 is actually legitimate proxy for the remote object. Okay, that's a proxy. By the way, some of you might already thought about this. Let me ask you a question. Can a real object, F1, has more than one shadow object? I'm actually asking the class. Can you have another one? I call it SF11, which is also a shadow object, but it's actually pointing to the same real object. Can we have that?
No.
Why not?
Because each shadow object should represent one real object.
Okay. So
because they have the same characteristics.
Okay.
Yeah.
It depends. It depends on what you like to accomplish. It depends on what you like to accomplish. If this particular object, the real object, is something which is very personal to me. For example, my credit card number, or my house, or my something, or my family member, it's very unique. Then in some sense, I want to have only one proxy representation, right? I want to have a one proxy representation if you want to talk to this object, you have to go through me. So I am the only agent. I'm the only proxy you can use to communicate with the real guy. And that's for certain application, that's great. On the other hand, in certain application, that I might be able to create multiple proxy, which means that Saeed, on your mobile phone, you actually create a SF1, which is pointing to F1. And on my cell phone, I also have SF1 that pointing to exactly the same object. What does that mean? It means that people can, the application program can go through either your smartphone or my smartphone, and we can actually interact with the same object. In fact, it's actually in real world, you can see that some of the real objects, they can simultaneously entertain multiple requests from different parts of the world. They can interact. So depending on what we want and what we have, and the design doesn't restrict that we have a multiple proxy that's actually simultaneously pointing to the same place. And in fact, of course, there are challenges. For example, one of the challenges you gradually realize whenever you have this distributed setting, you have to worry about a term which you will probably learn that when you take a upper division course. It's called concurrency control. Concurrency control, for example, that fly object is a bank account. You allow Saeed to withdraw $5,000. You allow Felix to withdraw $5,000 from our smartphone. And well, the bank needs to make sure that the account does have more than $10,000, right? So there is some kind of concurrency control, means that if you want to allow multiple assets, that means you want to allow people to be able to see that multiple assets will not introduce some harm to the application itself, okay? So I just want to tell you that it depends, but certainly this architecture does not mandate you can only have a one proxy. It's a proxy you think about is just telling you, okay, I can help you to forward it. That's the second function. The first function just give the information about where that real object really is. And the second part is that, okay, once you know where it is, then you can call the function. You can call the function. When you call the function, you really call from the application program, for example, get distance. So I'm actually calling from application, but the application, when they issue the call get distance, they really don't know whether that pointer to the fly object is really a shadow or is a local. In fact, it shouldn't care. It shouldn't care whether it's a fly in most applications, because as long as the result is correct, and I shouldn't care whether this object is actually local or remote. In fact, in a lot of distributed system today, sometimes it's better for you not to know where it is, because, for example, if you have some internet outage in certain region, if it's just unlucky that your resources is being affected, then there is a notion called object duplication, replication, or object mobility, that you want the object to be moved to another place, which you actually still be able to access, and then you can continue your computation. So you think about today's programming, from the programmer perspective, they shouldn't worry about precisely where's my resource. I just want to know, I want to access this resource. And everything behind this green line is real plumbing that they will connect you to the real machine. So that's the spirit about how do you provide a large scale system to not just about you can distribute, but distribute it for robustness as well, reliability, because you don't know what happened. I mean, if you know how big company, cloud company like Amazon or Google, they build their computational environment, you probably know they have a lot of redundancy because they don't know. They use, the idea is that we move away from mainframe computer, which is very expensive. We use this, what we call commodity hardware, one of the problem with commodity hardware is that it will fail. It will break from time to time, and therefore you have a massive amount of hardware around the world to do the computation. You're expecting as a norm that many of them will break any day, and so when that happens, they have a way to recover. And one of the way they recover is actually shuffling around the resources, such as the example we're talking about here. Okay, so that's we think about really what we're doing is like this kind of scenario. Okay, so now I'm actually going to go for the homework I haven't talked about last week. Is that, well, if I actually have one proxy, which is from SF1 directly to F1, I mean, I could have things like this. I could have SF1, it's actually pointing, it was at the last minute, it was actually pointing to this one. But then say there's a one part the server failed, and I no longer can retrieve the real object, the information. And therefore what I did is, okay, I know I have a copy in another location. And what I did is I immediately create another proxy over here who knows where that backup is. So then your machine will actually talk to itself is a proxy. So you can have a proxy, talk to the proxy, and then reach the real object. In fact, this could be a chain of proxy before you can actually reach out to that information. And this in industry, by the way, happens a lot. Of course, we want to manage this kind of chain of proxy very carefully. Number one is actually going to be slower because the least hop that you can have, and it will help you to actually be able to get your computational done. But sometimes temporarily, because of the system failure and other thing, and sometimes you want to build up that chain to manage such that you can actually, for that moment before the system was fully recovered, and you will be able to access to that. Okay, so that is the application I like you to build. So previously, this picture, you can think about this part is client, and this is a server, right? You have a client server. But I want you to actually be able to write a program. Think about that is essentially write another program, which this is the client and this is a server. But the server is also a shadow. But the server is actually pointing to another copy of the object. And such that you will see that your client is talking to the server will forwarding over here. So here is a beauty about encapsulation, about the design. The way you design is that the interface between these two, by the way, I said that the interface between the SF1 and F1, they are from ecs36b, HW3.json, and using JSON RPC to generate HW3 client.h and HW3 server.h. And when it received by HW3 server.h, the HW3 server.h treat that based on the object ID, class ID, and the URL. It basically point then to a pointer to the fly object, right? It's a fly object pointer. If you remember the code, I use F1_PTR. If it's F1, if it's a fly pointer, then it's the same thing about encapsulation, because if it's a fly pointer, I don't need to know, which is the HW3 server doesn't need to know whether this is a shadow fly, or is a fly. So in some sense that this model here, when you deliver this call, there's nothing in your code that mandate that this one can only be the real fly object, can not be the shadow fly. Because shadow fly, remember, encapsulation is also a fly. And therefore, when we do this, it's really just copy. Let me tell you that. You're really just copy your code, HW3 server .cpp into HW3 another .cpp. So these two, the code base, are basically the same. The only difference about this two pieces of code between HW3 server and HW3 another is in the main function, because remember the HW3 server is the main. In the main function, you need to decide what is the locality of your object. Is this object you put it in HW3 server is a shadow or is a real object? So that's the placement of object. Once you place that object in their respective location, then basically is you just abstractly just call the first level object. It should automatically route it to the second level. If it's real object, you're done. If it's not real object, it's a shadow, the code will actually call get distance, and that get distance on the server is also a virtual function. It will find out that get distance need to result in another place. And the result will come back from the remote to the server. The server will get the real distance number, and then they will return back. So this can actually go multiple layer. I'm just asking you to do 2 layer, basically from client to the server to another. But you can imagine the same software base is so powerful, you can do as many layers as you want, as long as you manage the what do you call that? The forwarding, which is those 3 characters, the URL, class ID, object ID on each of the program correctly. If that is correct, that basically say that where is a real object really located, and then you will be able to write that program. If you're done with this part, which we actually covered already last week, if you have any question, you can ask me immediately. But from here to here is actually not very difficult. You just need to do a little bit twist, but not twist for the main part of the server. It's just twist for the, the main function of the where you actually create those fly object, shadow person, and the person object. Okay. Okay. I think I will. What you really want to implement is like this picture. I'm going to skip this part. It's something looks like this. Okay. From the client to the server, and then to the another. This kind of scenario. Okay, and I mean, regardless, you have a function such a member function such as operator equal, which you take the parameter, or get distance, which you don't have any parameter. You just need to get the result. So regardless, I mean, it's the same way, same mechanism to do that. Okay, I'm going to stop here and let you ask some question.
Professor?
Oh.
Hold on 1 second. Yes, please, go ahead.
Are we like in a, sorry. So I missed my small program, like the meeting, like it was last Friday and I missed it. Like, what can I do to like make it a
smaller group, right?
A smaller program. It's called smaller program. It's on Friday. I'm in group 6, I think.
Yeah, it's called smaller meeting. Yeah, smaller group meeting. That's okay. Yeah, okay. I'll send you a link. Then you can attend today if you'd like to.
So speaking of small programs, sorry.
Sure. Yeah.
Speaking of small programs, how many small programs are we supposed to submit?
If you submit more than 20, you will get the full credit for that 20%. Totally, there were about 34.
Okay, so are those the exercises at the end of each chapter?
I actually select, not all of them, but I select those which I think representative from chapter 11 to chapter 14.
Okay, where can I find it?
It's on the syllabus, bro. It's on the syllabus. You can find a link there and then just go there.
Okay.
You have, yeah.
Is it okay? Okay. Okay,
It's
thank
on
you.
the syllabus. Yeah, no problem.
Okay, so any question regarding what I just talked about for homework assignment number 3 so I want to make sure that people have a chance to discuss about homework assignment number 3. Any question regarding homework assignment number 3 at this moment?
I have a question.
Sure, Fred.
So if we wanted to compare, like, say, an object from server 1 and an object from server 2, but say like server 1 has a shadow to the object in server 2, right?
Mm-hmm.
If you were to like do the comparison, say it happens in server 1, would like how would you get like the information from the shadow object on server 1 in regards to the real object on server 2?
Okay, let's Fred, that's a good question. Let's use the example operator equal as an example. So operator equal is essentially the equal sign has two objects, one object on the left-hand side, one object on the right-hand side.
Yeah.
And the design is the left-hand side object is the one who's going to do the real comparison. And what if you see the operator equal, that the right-hand side is a person, right? The a person parameter. So essentially, you are executing this code operator equal at the real location of this object. And and then you basically call the a person to retrieve the information using whatever the virtual function. For example, get VSID. That's why we have the get VSID as one of the location. I mean, that's a good question. Let me actually write it down here. I want to tell you that I think this question is really good, and it could be really confused. So let me actually go this way. I want to share my screen so you can see what I'm doing here. Can you see my screen?
Yeah.
Okay. All right. So all right. So assuming we say HW3 server 1 has this object person 1. Okay. Assuming, and HW3 server 5 has this object person 7. Okay, assuming that's the location about the real object. And the statement we would like to compute, we actually compute on HW3 client is really want to compare person 1 equal to person 7. Assuming that's the, let me actually change the font to be mellow, because mellow is better to show the code. One of the problems is I have to get to M.
Are you going to talk about the web reporting?
Yes, I will talk about web reporting.
Thank you.
Okay, so so we have this scenario. The objectives. Our objectives is at HW3 client, we want to compute this function, right? And then the location for real object is like the following. Okay, so this is given to us, and so let's see what's happening here. So over here first, what I will do is that if I assume that the real object is a person HW3 server 1 person 1, then essentially what I need to have is that at the HW3 client, I must have a shadow person 1, and I must have a shadow person 7. Okay, I must have this too. If I don't have this too, I cannot do anything. So at the client, you must have that. But then you're going to call it. When you call this operator equal equal, the way you call it is operator. It becomes translate to the code, the virtual function, operator equal equal. And the parameter is going to be shadow person 7. I mean, it's really person 7, but it's really a shadow person. Okay, so what I'm saying that the code might looks like person 1 is equal to person 7, but when they created it was a shadow one. Okay, but this operator equal equal was, oh sorry, this is a 7, not 1. Okay, and the thing is that the object that's actually get called for this operator equal equal is actually shadow person 1. So essentially it looks like this. It's shadow person 1 dot operator equal equal, and the parameter of that operator equal equal is shadow person 7. Okay, that's how it got translated into there. So far we haven't actually talked about the remote object. This is actually happening still in HW3 client. But when you really make this function call, that's actually the whole thing. Now I'm going to mark as the red. Will get delivered to HW3. Okay, so the red now go to using remote RPC, go to HW3 server 1. Let me actually make a color. Red to HW3 server 1. Why is that? Because the shadow object for person 1, it should actually redirect to the HW3 server 1 because HW3 server because person 1 is over there. Okay, so now you're actually getting it. Now you're going to write down the code. The code of operator equal equal looks like this. It looks like if this to the, let me just write down this very quickly. VSID is equal to a person dot get VSID. Something like that, right? I mean, some code looks like this. It is really the implementation of operator equal equal in your homework assignment number 2. But now we're already in homework 3 server 1, so this part has no problem. This one we already have. But this part is interesting because here we have a get person, and I'm going to turn that into red again. And this is also a virtual function. And by the way, I should actually say that at this moment that a person is actually shadow person 7 also on HW3 server 1. Okay, so this is also a shadow. And the thing is that this one on server 1 is actually, this is on server 1, but it's actually pointing to server 5. Right? I mean, now we're actually, I should basically say we are at, okay, we're at HW3 server 1. Okay, so now we have this. So now we're actually not doing the call for operator equal equal. We're actually calling the function get VSID. But then that get VSID, I will use a different color now because it's a different function. I will use green. Okay, And now the green is being redirected to HW3 server 5. Okay, so now I'm going to change this to green.
But Professor, I think the key question here is that are we supposed to then compare the VSIDs of each flight, of each shadow flight? For example, compare the VSID of F2 and F3 in our case?
No, you don't have to. It's just an example, right? I mean, it depends on what we want. I mean, this is an example. If your test program is actually compare the person, two person for whatever. I mean, this
Okay.
I'm explaining to you is an example about you can do any kind of comparisons you like. You can do any kind of comparison that, sorry, maybe I misunderstood your question.
No, but my question is, for homework, are we supposed to compare the VSID of the two flights? Is this what we're supposed to do?
If your main function
Mhm.
have this line that comparing the flight for some function, the flight will have the function called conflict of interest, right? The
Mhm.
conflict of interest, if you want to implement the conflict of interest, the conflict of interest will invoke operator equal equal for two person.
Okay.
So I don't think we have any, we don't compare any two flight. We either calculate the distance about the flight, right?
No, because each flight has its own original VSID, something like this. It's its own attribute. It's called wait, yeah,
Flights don't
it's
have
called
a VSID.
No,
it's called it's called owner VSID. The flight has a VSID. It's called owner VSID.
well, over here we're talking about a person. So we don't have actually any, if you look at the code, we don't have any places that you compare the owner's VSID. We only compare a person, the VSID between these two person. So let me actually explain to you. See, when I talk about how do you uniquely identify an object, I only talk about class ID, object ID, and URL. I didn't say owner's VSID. I didn't say that, right? But there are 4 elements. I think you're very careful. You look at, there's owner VSID. And that is actually used for something else. So owner's VSID is that who actually own this object. So we haven't actually talked about object ownership because we didn't have the object ownership in homework assignment number 2. So I didn't do that, but I actually have a placeholder for doing the owner's VSID. That means which user or which student in ecs36b class is actually on that object. That parameter is for. But in terms of the logic, the application, owner's VSID does not play a role here.
So for this homework, we're supposed to compare the agent and the person.
Right, the agent and the person.
Right. This is the comparison that we need to do. Okay.
Exactly. Yes. Yeah, it's in terms of the logic, it should be the same as the homework assignment number 2. Okay. Any other question? Okay, so so far this example, I just want to finish this example before I close this for today. Is that now you go to the green, and similarly at homework 3 server 5, which is the place, then you are going to call get VSID. But this get VSID is get the A person's VSID. And the whole thing, once you get VSID, you will be sent back to homework 3 server 1 over here. Let me actually just draw an arrow here so you know what I'm talking about. So this one will actually get back here. All right. And then from here, now you have all the information. Now on homework 3 server 1, you can really compute this particular step. And now you complete the operator equal equal, you return the result back to HW3 client. And then they will be able to continue to do the computation. you can see that it's really could have put everything in one single program, but now we're actually computing this 3 function on 3 different machine. And because the object localities are different. I mean, the most complicated one is operator equal equal, because the A person and the left-hand side and right-hand side, person 1 and person 7, they're actually on 2 different machines. And that's actually interesting, because if you can handle this particular case, I think you can handle any case for distributed computing like this, okay, using the same piece of code to do that. Okay, all right, so our time is up right now. I'm going to shift into the extended session. I'm not actually going to post today's link over here, because I mean, I have already done 6 sections from group 1 to group 6. I mean, the first time I restrict the access, only those group member can participate, but I feel that we have a room for those. So I'm going to post it here. If you want to join, you can join, okay? So I'm going to, let me actually just post it very quickly. Let me first stop recording, and then I will post it.